It's green, though, so that's a good sign. Hi, everybody. Okay, I got sound. Good. So today's lecture is not on midterm 1. You may notice it's less busy. Maybe you didn't know that. Welcome. So today I'm going to be talking about the first beginning part. I'm going to wrap up counting, and then I'll turn it over to Manuel to talk about fancier counting, I guess I'll call it. So last time we saw that we can use our counting problem solutions to help us write proofs. I went through very briefly, and I don't think necessarily super well, a proof of the binomial theorem. I'm going to show you one more small example, followed by a larger example. The small example I'll do first. I'm going to kind of race through it. It'll be pretty fast. If you don't get it, it's not that hard to digest and look at later, but I want to do this first one pretty fast, which is to say, let's suppose we wanted to show this seemingly, totally arbitrary fact that 2 to the n is equal to n choose n plus n choose n minus 1, all the way down to n choose 0. So I can plug in some numbers. For example, I choose n equals 4. In that case, 2 to the 4th is 16, and indeed 4 choose 4 is 1, 4 choose 3 is 4, and so forth. And it works out. Okay. Why do we care about this? It's just a little toy problem. That's the only reason. Okay. So I want to show this holds generally. And the way I'm going to do it is a very common thing with combinatorial proofs, which is I'm going to count the same thing in 2 different ways. So I'm going to count something in one way, which will give me 2 to the n, and I'll count that same thing in a different way, and it will give me the right-hand side. So what am I going to count? I'm going to count subsets of 1 through n, and that's just arbitrarily the example that I chose. And so on the left-hand side, if we think about counting subsets, we know there's 2 to the n possible subsets. Why is that? Well, each subset either includes or does not include each of my integers. So for example, and this is just what we saw before, which is the first rule of counting. We have a bunch of binary choices. Include yes or no. Include yes or no. We're doing it with replacement, so we get 2 to the n possibilities. Another way of thinking about it is the subsets, for example, for n equals 3 are no, 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 yes, no, and so forth. So clearly there must be 2 to the n subsets. That's the left-hand side. Okay? Let's also count all the subsets in a different way, not just thinking about the first rule of counting, just a different, like turn my head sideways and try and count it. Okay, so how do I do that? Well, I could say, well, how many subsets are there of all of the items? So if I have n things and I form a subset of all of them, how many subsets are there? 1, right? It's all the items. What about all but one item? It's n choose n minus 1. Why is that? Because you have n things and you're choosing to use n minus 1 of them. So that's n choose n minus 1. Here they are for n equals 4. Those are all the subsets of the integers 1 through 4 that include all but one item. How many subsets that include all but 2 items? N choose n minus 2, and so forth. And then lastly, how many subsets are there of just one item? Okay, well actually there's n choose 1. There's actually one more case, which is how many subsets are there of no items, because the empty set also counts where I include nothing. So if I just add all these up, that's the right-hand side, right? So these are 2 different ways of counting all subsets of 1 to n. One is to use the first rule of counting. The other is to consider individual sizes. And in that way, we get a combinatorial proof. Okay? So I went through that pretty quick, but it's just showing you this basic technique, which is count the same thing in 2 different ways. Okay? Sometimes it's handy. I will say that this particular identity is not very useful. I don't know of any place where it comes up. The binomial theorem, which we did last time, that one is a more useful identity. Okay? So basically the idea is we got the left-hand side and the right-hand side by counting the same thing in 2 different ways. We proved an identity. That's the whole story. In the discussion section and also in the notes, there's more examples of such simple combinatorial proofs where you prove kind of arbitrary identities just to get some practice flexing your brain to think about, if I wanted to count things in 2 different ways, how would I do that? Okay. So for the rest of today, I'm actually going to talk about, for my part, I'm going to talk about something else called the principle of inclusion-exclusion. And I'm not going to take any questions on this because this, I mean, to me, if you didn't get it, you could spend 5 minutes rewatching it later and you'll get it perfectly fine. Okay. That's not supposed to be there. That was the other one I was going to do. It's gone. Okay, so the principle of inclusion-exclusion, you've seen this before, this 2-set version for sure, which is if we have 2 sets, A1 and A2, and I want to know the size of their union, we know that the size of the union of those two sets is the sum of the individual sizes minus the size of their intersection. Okay? So these different pieces are, this is of course the size of their union. These bars say size of set. This forms a new set, which is their union. And these are all the individual pieces. So for example, if A1 is A, B, C, and D, and A2 is C, D, E, and F, if I wanted to know the size of the union, it's 6, right? If I union these two sets, it's all 6 items. And what this formula tells us is how we can compute the union's size from the individual set sizes and the intersection. So the sum of the individual set sizes, how big is this one? 4. This one, also 4. And then how big is their intersection? What is the intersection of A1 and A2? C and D, size of that is 2. And so the formula works. Look right here. See, we just take the size of the union is the sum of the individuals minus their intersection. And the argument for this is this old Venn diagram you've seen before, which is if I have two sets, A1 and A2, and I add up the cardinalities of these sets separately, I've double counted their intersection. So the way I fix the double counting is then I subtract the number of items in the intersection. Okay? So hopefully this is pretty familiar. And so what we're going to do in the next 18 minutes or so is try and show a formula for what happens if we have more than two sets. So we'll start with 3. Let's say we have 3 sets, A1, A2, and A3. We might say, okay, what we got to do is add up the individual sizes of the sets and then subtract out all the intersections. But there's one little issue here. Anybody spot it who's not a Math Olympiad person? Yeah?
Aren't we, overcounting that intersection of A1, A2, and A3?
Yeah.
We're like triple count. No.
We triple counted it. That's right. And then we untriple counted it. So what actually ended up happening at the end of the story? Well, any particular item in here, we counted it once for A, once for A1, once for A2, and once for A3. Then what happened? We subtracted it out 3 times.
And so now we don't have that center.
Right, exactly. So the center, what happened is we triple counted all the points in the middle. Then we subtracted them out 3 times. Once for this intersection, once for this intersection. And that meant we didn't count them at all. And if you're not totally convinced, just write out a small example after class. And then convince yourself that what happens is if you subtract out these pairwise intersections, you end up counting these items 0 times. So how do we fix it? Suggestion? Just add that back in. Add in the size of that intersection. Okay? So in other words, we have a formula now that's a little messier than the one you were already comfortable with, where before you add the separate sizes and then you subtract the intersections. Okay? Now we add the individual set sizes. Then we'd subtract all the pairwise intersections, good, to avoid triple counting. But then we have this issue, or double counting, right? That fixes the double counting problems, but it over-fixes the triple counting problem. So then we need to add these centers back in. That's the principle of inclusion, exclusion. I'm guessing many of you have not seen this. Hopefully the visual picture works. And again, you can convince yourself with a small worked out example where you pick some letters for A1, A2, and A3, and maybe that will fully convince you if you're not happy with the diagram version. Okay? All right. Another way to think about this formula is let's imagine a point X that belongs to all 3 of the sets. Okay, ooh, this should be an intersection. I knew there would be somewhere a problem. Okay, let's fix it. Okay, cap. Okay, and they could be the wrong color. That's okay. That's a penalty I pay for having a typo. Okay, good. So let's say now it took my animations away. So you have too much stuff to look at. Apologies. So let's imagine a point that is in the intersection to all 3 sets. Okay. So what happened was X was counted in each of the sets, right? A1 plus A2 plus A3. When I did that sum, X got counted 3 times, okay, because it was in all of the sets. So we overcounted X. Then X was in each of these sets as well, because if it's in the intersection of all sets, it's certainly going to be in any of the pairwise intersections. Because if you were in A1 and A2 and A3, you're also in A1 and A2, and you're also in A2 and A3, and you're also in A1 and A3. Okay, when I say and there, I mean intersect. So that means we now have subtracted these 3 out. And then lastly, it counts 1 here. Okay? So in other words, we did 3 minus 3 plus 1. We can also observe a pattern here, which is that we can think of x, and again, sorry, these should be caps, not cups. These are intersections, as belonging to 3 non-intersections, right? It's in all of the sets separately. It belongs to 3 pairwise intersections, and it's also in 1 3-way intersection. And that's what the principle of inclusion-exclusion formula gives us. Okay. All right, let's keep going. We can keep doing this, and without proof, I'm going to offer a procedure that if you had 4 sets, you could do the following. We could add all of the, so we want to know what's the size of the union of these 4 different sets. We add up the size of the individual sets, but that's an overcount, right? We've overcounted items, because some things are going to be in more than one of these sets, and so they're going to count in both. So if I have some specific item that's in 1 and 2, now you've just counted it twice. So now what we're going to do is subtract out the pairwise intersections. Okay, so there's more pairwise intersections when you have 4 sets, but that results in an undercount. So we're going to add back in the sizes of the 3-way intersections. Here they all are. These are the 4 different 3-way intersections, and that results in an overcount, so we'll subtract out the size of the 4-way intersection. I have not proven this to you, but hopefully it seems at least plausible based on the pairwise case, which fits in your brain comfortably, the 3-wise case, the 3-set case, which fits with some stretching, and now is just like pattern matching. Okay? But our goal is going to be to try to show that this actually holds, and it keeps going. Okay? Hopefully the feeling here is good. Yeah?
Wait, isn't the intersection of like 3 already included in this individual subsets of A1, A2, A3, A4?
Are the say one more time? Just say.
You know when we do A1, like
Yeah, this set right here?
No, the top. So
Up here.
Yeah, here, right?
Yeah.
So we add those. Like my question is, why do we have to add the intersection of A1, A2, and A3?
Right, so these are the items. These ones we undercounted when we subtracted out these pairwises. So the intuition is that there are items that we counted, we overcounted here, and then here we tried to adjust for the overcounting, but then we forced an undercount, and then this is fixing that at the next stage. So I mean, I can't, that's the shortest version I can give you, and maybe as we evolve through the longer proof it'll make sense, but yeah. Okay. So I'm going to give you a different version of this formula. Okay, it's going to be a more compact representation, and it looks something like this. So it's just going to be for 4, same things. I'm just taking this and writing it in a nicer way. I'm going to say that here I have, we want to know the size of the intersection of 4 different sets, and that's going to be -1 to the k minus 1 times this thing called intersect sum k. Okay, let me talk through these pieces here. So what intersect sum k is it's the sum, sub k I guess I'll call it. It's the sum of the size of all k-wise intersections of the sets. Let me give you an example. Intersect sum sub 2 is the sum of the size of all the pairwise intersections. So here's a pairwise intersection. There's one, there's one, there's one, there's one, there's one. Okay, that's all of them. Okay. What about intersect sum 3? Okay, well that's going to be these 3-way intersections. And am I missing anything? Are there any 3-way intersections you might observe or not around? There's one. 2, 3, and 4. Okay, so we missed that one when I first showed it to you. And that right there is all, it's a sum of the sizes of these 3-way intersections because I picked k equals 3. Okay? So let me convince you that this formula, unproven, but let me convince you that this formula is what we had before, right? This formula right here is the same as this one right here. This is the sum of the individuals minus the sums of the pairwise sizes plus the sums of the 3-way sizes and so forth. It is the same formula, right? Because each of these intersect sum sub k's just gives you back, like intersect sum sub 2 is just this sum of 6 different combinations. And then what's this -1 to the k minus 1 doing? It's flipping signs. So first it's positive signs, then it's negative signs, then it's positive signs, then it's negative signs. Okay? Now again, I have not proven that this works, and maybe that's kind of what you're getting at. Like, isn't this, I haven't shown you that this is true. I've just given you a plausible pattern, and now I want to try and show that it is true. I'll let you stare at this for a second. Or anybody have any questions about what the formulation of the problem is? Okay. This is an interesting exercise for those of you who like to write down everything on the slides. There's too much to write, so hopefully you're writing things in a more compact way. Okay, because I like to unroll it on the screen, but if you tried to write this down, it wouldn't be fun. All right. So now I'm going to try and prove this. This is the principle of inclusion and exclusion for any number of sets. And I'm just going to generalize. I'm going to say instead of 4 sets, let's just do it for n. Okay? Like hopefully it works. I'm going to prove that this works for n. And my goal is to show that this formula counts every element exactly once. This is a subtle proof. And the presentation in the notes is incredibly dense. So my sub-goal here, I'm going to prove that this formula up here correctly counts items that belong to 4 sets. That's going to be my sub-goal. I'm going to start with just, like, imagine an item that's only part of 4 sets. I'll show that it counts that correctly, and then I'll generalize to items that belong to any number of sets. Okay, so let's jump in and do it. Okay. So quick warm-up question, and I'm not doing any polling questions because I want to make sure to give Manuel the time that they need in order to get through the other counting stuff. But here's a question. So how many terms does intersect sum sub k have in general as a function? So we have n sets, and we're going to add up the k-wise intersections. Any thoughts? Yeah? N choose k, right. So for example, if we have n equals 4 and k equals 2, so that's what we saw before, we have 4 different sets, the red one, the blue one, the green one, and the black set. And we're adding up all the pairwise intersections. So how many different ways are there of forming pairs? Well, there's 4 choose 2. Okay, so that's why it's n choose k. Okay, or in this case, 4 choose 2. Okay, so warm up. All right. Okay, so now what I'm going to do is I'm going to imagine an x, which is in set A1, it's in set A3, A6, and A8. And why those? I don't know. I just picked 4 arbitrary set numbers. Doesn't matter which ones they are. But x belongs to those 4 sets, and I have 54 sets. That just somehow makes me feel better, right? It's not n sets, it's 54. And so I want to know how many times does x get counted when we do all these intersect sums, okay? So we're going to ask this question. For each x, how many times is it counted in intersect sum k, sub k? And I'm going to start with intersect sum 1, okay? So when I have x, if x belongs to these 4 sets, how many times does x get counted when I add up all of these here? Okay. Intersect sum 1, I should say first, it's possibly some giant number, like 286 million. I don't know what it is. But how many of that 286 million does x contribute? 4, right? It's counted 4 times because it belongs to set A1, A3, A6, and A8. X is being quadruple counted. Okay. This is kind of obvious, but kind of tricky, right? Like, why do we care about that? Well, I'm trying to show you that x gets counted the right number of times. What's x? It's some item, any item, that belongs to A1, A3, A6, and A8. And what I've just shown is that intersect sum 1 overcounts that. Okay? What about intersect sum 2? How many times is it counted here when we call intersect sum 2? And this is probably the most interesting slide of my part. Like, if you get this, I think you understand the most important part of the day. What do you think? How many of these sets does x belong to? So does it belong to A1 intersect A2? That's an interesting question. So it only belongs to these sets. It does not belong to set A2. So does x belong to A1 intersect A2? No, it's not in there because it's not in A2. Okay, so not that one. How about A1 intersect A3? Yeah, it's in there. A1 intersect A4? No. So how many sets does it belong to out of all these possibilities? 6. There's 6 of them. Because you have 4 choose 2. You have 1 and 3, 1 and 6, 1. Really, so. I started with 4, I subtracted 6, and now I'm at negative 2. So I'll call this a 3, but whatever. This is a little confusing. But we started with 4, we subtracted 6. Okay, how about intersect sum 3? I'll let you think about this one for a second. I'll cover my ears. Okay. How many times does it count? How many of these sets does it live in? I like 4 choose 3 as an answer. So what's one of the sets it belongs to, somebody? A1. A1 intersect A3 intersect A6. Indeed. And so it belongs to exactly 4 sets, because there's 4 different ways to leave out one of the items, or 4 different ways to pick 3 of them. Okay? So x is counted 4 times and intersects sum 3. So we started with 4, then we subtracted 6, then we added 4. So we're still double counting x. Okay, any questions about this idea so far, what we're doing? Okay, intersect sum 4. How many times does x get counted here? How many sets does it belong to? 1. Which set? A1 intersect A3 intersect A6 intersect A8. That's the only one. So x gets counted only 1 time. What about intersect sum 5? How many 5-way intersections does it appear in? 0. Okay. So here's a little table of what we just derived. We showed that for an item that belongs to just 4 sets, when we look at intersect sum 1, it's going to get counted 4 times, then 6 times, then 4 times, then 1 time. How do we translate that into what this formula purports to compute? Well, we multiply it by minus 1 to the appropriate power. The first one is 0, then it's 1, then it's 2, then it's 3, which, of course, we just take these odd powers and put a minus sign. 4 minus 6 plus 4 minus 1 is 1. So in other words, what we just showed is that for any x that belongs to exactly 4 of the sets, these ones, for example, or any other set of 4 sets, our formula counts that item once, which is great. It's supposed to count everything once. It counts items that belong to 4 sets exactly once. That's the basic principle. If you understand this, this is most of the proof. If you get this, this is the important part, and the rest is kind of bookkeeping. Okay, but let's do the bookkeeping. So what we just showed is that if x belongs to 4 sets, it's just some element of this union here, that it's going to get counted 4 choose 1 times in the k equals 1 intersect sum. It gets counted 4 choose 2 and k equals 2 and so forth. And you'll notice the pattern. We go up to, what's the biggest exponent for the minus 1? Yeah, 3 in this case. And if we picked a different number of sets that you belong to, say you belong to m sets, what will be the biggest minus 1 here? Minus 1 to the m minus 1. Okay? So we could just generalize this pattern, and I'm going to say, okay, the number of times that an item gets counted if it belongs to m sets will just be the same thing. Like if you pick m equals 5 and you repeat the same exercise, you'd find it's m choose 1 minus m choose 2 plus m choose 3 minus m choose 4 plus m choose 5, and that will be the number of times it gets counted. Okay, so if we pick m equals 4, we got 1. If we were to choose m equals 5, the number of times it gets counted would be 5 choose 1 minus 5 choose 2 plus 5 choose 3 and so forth, and that also turns out to be 1. Okay, so this is a proof that an element, or that an item that belongs to exactly 5 of the sets also gets counted once. So that's pretty good. Now we haven't shown that an item that's only in 1 of the sets or in 85 of the sets or whatever, they also get counted once. But we know that it works for m equals 4 and m equals 5. Okay, so we just need to generalize this and basically show that no matter what m we pick, that this sum evaluates to what? 1. So this function should be 1 for any m we choose. That's what we want to show. Okay? All right. So basically, this sum, if we show that we already showed that it works for m equals 4 and 5, we want to show that it works for any m. And so we're going to see a really clever way, and this is a quite mind-bending trick that uses the binomial theorem, which seems totally unrelated. I think this is a super clever proof, and I'm going to give you a short version of this. I mean, I think it's the whole story. But we can use the binomial theorem to show that this right here is always equal to 1. It's a pretty clever and cool identity, but tricky. Okay. All right. Now, I should note that this is way beyond the scope. To realize, out of all the things in the universe that I could pluck from a hat and use to solve this problem, this is not obvious at all, but it's very cool. And one of the things that really good mathematicians have is a really big toolbox that they know how to access and figure out what to apply. I am not one of those mathematicians. Manuel was a mathematician. I was a dilettante in biology of some kind. Okay. So this is how it works. So let's suppose we plug in a equals 1 and b equals minus 1 into the binomial theorem. Okay, this is the binomial theorem. If I plug in 1 plus minus 1, what happens here? 0. Okay, so great. You showed, okay, you plug in 1 minus 1, take it to the nth power, that's 0. Okay, that's a very fancy 0 you've got there. Well, what's nice is that on the right-hand side, if we plug in a equals 1 and b equals -1, this will also be 0. Okay, so we plug in a is 1, so a to some power is just 1, and then -1 to the k. This whole thing is going to be 0. Now, it's not obvious that this would be the case, but the binomial theorem tells us this. And then I'm just going to mess with the binomial theorem a little bit, and I'm going to convert it into the format we saw earlier. Okay, so how I'm going to do this is I'm going to write it out. I'm going to expand it. So hopefully you agree with me that this is the appropriate expansion. I plug in 0, I get this. I plug in 1, I get this. I plug in 2, I get this, and so forth until I get to the end. Okay? The next thing I'm going to do is I'm going to say I'm going to get rid of these even powers of -1, because what's -1 to the 0? 1. Okay, -1 squared is also 1, so let's drop those. And then let's turn these into minus signs. So if you're an odd power of -1, I'll turn you into a minus sign, and when I do that, I get this slightly different formula. So it's just the same thing, it's just now alternating pluses and minuses, starting to look familiar. And then notice I didn't toss or convert the last one, because I don't know if it's even or odd, so I'll just leave -1 to the end, okay? All right, this is starting to look a lot like what we were trying to prove. I'm going to get rid of this part. I don't need this anymore. And I'm going to say, we know that 0 equals this particular sum. So we're really close. Question, what's n choose 0, do you think? 1. So if you have n things and you pick none of them, how many ways are there to do that? Just 1. There's one way to choose nothing. So I'll put in a 1 there. And then I want to set all of this stuff equal to 1. So I'm going to do that by adding n choose 1 to both sides. Okay, there we go. Now I'm going to subtract n choose 2 from both sides. And I'm just going to keep repeating that process. And when I do that, the last step is I'm subtracting n choose n times -1 to n, right here. I'm going to subtract this from both sides, and we end up with this right here. I just subtracted it from both sides. And then the last little algebraic trick is I'm going to say, I really want this to be a plus sign. So if I turn this into a plus, what do I need to do to this exponent? I could -1 it, or I could +1 it, but I'm going to do -1, okay? So I did a bunch of algebra quite fast, but hopefully each step, even if you couldn't string it all together in your head, you said, okay, yeah, the binomial theorem got me to show that this thing is equal to 1. And that is exactly the thing we were trying to show is 1. So it's kind of wild to me that the way, so this proof is pretty involved. There's 3 big steps. One is first realizing we want to prove that every item gets counted exactly once, no matter how many sets it belongs to. We derived a formula that says how many times we count an item as a function of the number of sets it belongs to, and it looks like this. In class, we just arbitrarily went through the case where it belongs to 4 sets, then 5 sets, and we said, hey, it equals 1. Then we said we'd like all it to work for every possible m, and then weird side quest into the binomial theorem, we are able to show that this thing sums to 1. That's the short version of the proof. Okay, so this is about as fast of treatment as I think it is possible for this to be clear for some of you. And so I encourage you to rewatch, but I don't think I really have much time to try and go to the details, but I'm happy to talk after. So one quick note before I pass it over to Manuel. 3 quick notes, actually, on notation. First thing is I did everything in kind of expanded notation because I thought it would be easier to follow during lecture. You might try to use this more compact sigma notation. That's fine. If you do that, I'll note that then your side quest is the binomial theorem in this format, and the notes tend to stick to something more like this format. So they tend to use sigma versus the expanded format. That's just what I did. Now, if you try to read the notes, I do want to warn you that the notes skim over the fact that this expression yields this expression, and it's not totally trivial. So just be aware that the side quest, the thing I called the side quest, they call it corollary 10.1, and I find it harder to read than this version. But you may like this version better, especially if you're a very strong mathematician. So that's the first note. Second, I use this notation, which I made up, because I found it easier to read, which is intersect sum. This is the same thing that the notes do. And if you read this, you're like, okay, that's plausible. And I don't want to talk about it in lecture. But this right here is intersect sum. It's basically just saying the n-way, or the k-way intersection. So I made up this. I like it better. Maybe you like this better. This is a little more standard. And this is a funny thing in mathematical notation is sometimes the standard notation is hard to read until you get used to it. So I made it my own. And the very last thing I want to show is that the entire lecture I just did is this. Okay, everything I did except for the very beginning is just these 2 paragraphs for the most part, other than the corollary. And the way I did it, which I just want to talk about the notes for a moment, I walked through an example to develop intuition, to state confidently some particular statement, But the notes instead have this very compact and ultra-precise argument that is quite difficult to unpack. And so now that you've seen mine, maybe you can look at this and interpret it, but I just want to acknowledge this is very dense. And I just wanted to note something about mathematics, which is what Manuela said before, that math is having conversations with mathematics. And often those mathematical conversations get condensed into this hyper-concentrated form. If you ever read like a graduate math textbook, you'll see that they're really dense. They're extremely compact and precise like these notes. And that's good in some ways, because once you have the dexterity, you can read it and enjoy kind of unpacking it. But the downside, of course, is it takes lots of effort to unpack, potentially beyond your ability to find a toehold. I would not be surprised if many of you lack, I guess, the basics to be able to read this and figure out what's going on. Though I do want to note something that's new in the world is you can actually just give the notes to ChatGPT and say, like, I don't know, like, can you try something? Like, give me an example. I haven't tried this prompt, but you may find this kind of thing useful, which is like, give me an example so I can understand what the definitions even are. Because in formal mathematical texts, often the intuition is hidden, and you only get like the final compact brick of mathematics, and the notes certainly are that way. Okay, I do want to say one more thing, which is the notes talk about derangements. If you want to know about them, they're here. They are bonus material, though. They don't come up in homeworks, lectures, or discussions, and if you want to know about them, you could do them here. All right, I went over by 5 minutes. Sorry, Manuel. Okay, I'm going to hand it over to you. Good luck. All right, thank you. All right. Cool. Oh, right, master. Yeah.
Is this on? Hello? There we go. Taking a second to just get the board up there. Yeah, so while we do that, let me just say a few things about midterm. Thank you so much, Professor Hug, for taking over those lectures. That helped a lot with writing the midterm, so let's mention that for a moment. We'll talk more about the midterm on Tuesday. Today's Thursday, yeah. We'll talk more about the midterm on Tuesday. I do want to say that next week's homework, which would be on countability and computability, that's an optional homework that have time to study. Definitely study for the midterm. The homework's still good to do, but because the content will come up on the final. So have that homework in your pocket. That's good to have. Wednesday's discussion next week will be midterm review, so it won't be based on the lecture that happened on Tuesday. It'll be midterm review. And yes, we'll talk more about the midterm on Tuesday. I do just want to say that if you're looking at the previous midterms, there's spring 2024. That's Alastair Sinclair's midterm. That one is probably a closer match to a mental model of what this one will look like. I'm neither Professor Rao nor Professor Sinclair, so it'll be different from both, but the spring 2024 one might be a better mental model to have. Also, but doing Professor Rao's, don't get discouraged by those. He usually tells his class he can't even finish those in the amount of time. They're really meant to be like pick and choose. Choose the things you feel strong in, do the, like just kind of, you'll be, the average I think is often like 46% or something, but that kind of goes well within the bell curve. Everyone's just kind of like in there. He curves generously and the sort. But I just want to say, don't get discouraged going through Rao's. That's good, if you can do the hard version, you can do the easy version. So like going through Professor Rao's is good practice. So is going through Professor Sinclair's, but don't despair. Okay, so we have a lot to cover. So let's do that. So Professor Hug just taught a lot about counting today and Thursday. Forget all of it. I'm sorry, Josh. Forget all of it. We don't remember counting. We don't even remember what numbers are. So here's our warm-up question. You are letting goats out of a pen. You're letting the goats out of the pen, and you want to make sure they all get back in after they graze, but you don't remember how to count. You don't even remember what numbers are. All you have is a bucket, and you're standing on some gravel. How can you make sure every single goat gets back into the pen if you don't know how to count or what numbers are? Kind of a weird question, really open-ended, but any thoughts? Yeah.
No goats are outside of the
So no goats are outside of the pen. Let's say you're in like a little bit of a forest or it's hard to tell, maybe there's already some goats outside of the pen as well. You just want to make sure at least you have the same number of goats that come back in, even if you don't know what numbers are. Yeah? So the suggestion is each time a goat goes out, you could put a piece of gravel into the bucket. And then you do that for each goat that goes out. And then when it's time to come back in, you just take a piece of gravel out of the bucket. So now, if there's if you're missing a goat, you're still going to have gravel in the bucket. You know you're missing some goats. You need to go look for your goats because, and this is kind of an age-old way of counting without even knowing what counting is. You can do this even if you don't know what numbers are or you haven't developed numbers. And kind of the idea here is that, let's say this is your bucket. Again, bad drawings in math. This doesn't look like a bucket. It's a circle. But you have like rocks in your bucket. Let's say you have 4 rocks. We don't know what 4 is, but we can count them. And then you have 4 goats, Goats with 3 legs, I guess. But the point is, why does this work? It's because what you're doing by putting a rock in the bucket each time is you're making a connection. You're pairing each rock with a single goat. Because you draw this pairing, this connection, now you have kind of this correspondence between rocks and goats. So even if you don't know what numbers are, you do have a tie from the amount of gravel, rocks you have in your bucket to the amount of goats there are. So you can always use that correspondence to tell if you had each goat. So really, what you want is, yeah, we can see that up there. Each goat has a rock, and only one rock. So we'll come back to this later. That's our warm-up. We're going to switch a little bit now. Yeah, we're going to switch a little bit now. So, I'm the oldest of 4. I have 3 siblings. I'm the oldest of 4. And, we grew up getting in arguments, as siblings do. And, there's a bunch of different topics we argued about, but most of them really came down to the same thing. And even most of my arguments being an adult come down to the same thing. There's one side that says, yeah-huh, and the other side says, nuh-uh. And that's the argument, right? And you go back and forth saying, yeah-huh, nuh-uh, yeah-huh, nuh-uh. And someone finally says, yeah-huh times 10. And then the other side says, well, nuh-uh times 100. And then you can keep going. You could say, yeah-huh times 1,000,000, and then it escalates real bad. And finally someone says, nuh-uh times infinity. Then what do? They've really got you at that point. So how can you beat that argument? If you're having this argument, yeah-huh, on one side, and someone says, nuh-uh, on the other, and they say, yeah-huh times infinity, how can you even come back from that? What's something you could say on the nuh-uh side? Yeah. Yeah, you could say infinity. Oh, really escalating. If you don't want to, escalate the arms race that quickly, you could say, nuh-uh times infinity plus 1. And then they can say, well, yeah-huh times infinity plus infinity. And then over here you could say, well, nuh-uh infinity times infinity. And then you just kind of get into this never-ending arms race. And, the question here is, who wins? Really, are all infinities the same? Because you say infinity plus 1, but isn't just infinity plus 1 infinity? Is it bigger? Is an infinity plus 1 bigger than infinity? Can you have something bigger than infinity? I thought infinity is just everything, forever. How can you get more than that? Right. So let's talk about a little thought experiment. This is called Hilbert's Hotel. Hilbert is David Hilbert. This is around the turn of the 20th century. back in the early 1900s, there was a bunch of arguments amongst the metamathematics community of weird things happening. They were really trying to find the bottom of math. And the reason why we're talking about this will be more clear on Tuesday, because they're really trying to find the bottom of math. What does math rest on? What are the axioms? Can it be on solid ground? And the reason we talk about it is, one, it's fascinating and kind of the foundations of modern metamathematics, but also it's the foundations of computation. Because if you're trying to put math into a computer, it's not just intuitions anymore. You have to get it solid. And this is, like, computers kind of came out of the discussions happening in the early 20th century about different types of infinity, about which things are, there's deep connections between different types of infinity and the foundations of proofs and computation. So we're just going to start this today and kind of finish computability on Tuesday, or at least broach the topic. OK, so Hilbert's hotel is, let's say you have a hotel. Hilbert has this hotel with an infinite amount of rooms. There's room 1, room 3, room 4, and so on. Goes on infinitely. So infinite, but also there's no vacancy. Every single room is filled up. It's a really popular hotel. Every single room has a person inside of it. So now let's say a new person comes along and says they want a room in the hotel. Well, there's no vacancy. What are we going to do? You know? Yeah.
Move everyone by one room.
Yeah. So there's this trick. We can have, let's do a different color. We can have each person move forward one room. You can almost even picture it being on a loudspeaker, saying, in half an hour, everyone get out of the room and shift one over. And you can imagine everyone coming out of the room at the half an hour mark and shifting over one. And there's never going to be any collisions because it goes on forever. They can all just come out, go over one, and there's no double booking. It's kind of a wild thing to imagine, everyone just kind of coming out at once, shifting over, and then having a new room to themselves. But what it does is it leaves room 1 wide open for this new person to get in. So with this thought experiment, we're kind of seeing that infinity plus 1 is actually the same as infinity. So this na-ah argument isn't any better than that yaha argument. All right. So now we're going to do something a little bit more complex. Let's say you have the same thing again. Let's say you have the rooms 1, 2, 3. And again, no vacancy. Everything's filled up. But now you have a bus that shows up. And this bus, you know, bad drawings, is infinite as well. There's this infinite bus that shows up, and it's completely full. There's seat 1, there's seat 2, there's seat 3, there's seat 4, forever and ever. And every single person wants a room in this hotel. So the question is, how can we, if this is completely full up, how can we give each person here a room as well? Yeah.
You repeat the process infinite times. So you move everyone, like if one person gets off the bus, you move them by one, and then you just keep it.
So here's a solution. We could repeat this process an infinite number of times. We can move everyone over and someone comes in, and then again move everyone over and someone comes in. That would be an infinitely long process, but it would absolutely work. And we want to see, can we do this in one fell swoop? Yeah.
Move everyone who's currently in the hotel to the room that has double the number.
Okay. So there's this amazing thing about the natural numbers is because it's infinite, it kind of has infinite buckets within it. One of the infinite buckets is the even numbers. So there's this kind of suggestion. There's this suggestion where instead of someone moving over just 1, they can move to double. So 1 just moves to 2. That's fine. But 2 moves to 4. 2 times 4. Or 2 times 2 is 4. 3 times 2 goes to 6. 5 goes all the way to 10, and so on. And what happens is we have all the odd numbers being empty now. Right? So the even numbers get moved to. But because each thing that you're moving to is a multiple of 2. What's left over is the odd numbers never get filled up, even though they're left. So we can just put these people into the odd rooms. Now we have the even rooms filled up and the odd rooms filled up, and we have a full hotel. To say it a little bit more succinctly, or not succinctly, more precisely, let's actually say what this is. We shift 2 evens, and the odds are open as far as room numbers go. And what that actually looks like, I think I'll erase this. What that actually looks like is that room K goes to room 2K, and seat K, as in from the bus, can go to room 2K plus 1. So this is a thought experiment. We haven't done anything particularly formal yet, but are there any questions on this? Weird concept. Okay, where's my phone? Great. Okay, so what we kind of showed here is that infinity plus infinity is also infinity, kind of. Again, nothing formal yet, but we're showing that infinity has enough room to hold other infinities. The Hilbert Hotel, I think this will probably be on your homework, and you'll show that even if infinitely many buses, each with infinitely many seats show up, you'll still be able to seat them, which is kind of showing that infinity times infinity is also infinity. So, this is kind of a weird, informal notion so far. If we haven't thought much about infinity before, it's a weird concept. It's kind of weird to hold infinity in your head and try to reason about it. Let's try to get a little more formal. Because right now, we're talking about thought experiments. Let's talk about actual infinities. So what sort of infinite things do we know? Like, what's some set that's infinite that we know of? Yeah.
The reals.
The reals. Any others? What was that? Integers. We have the integers, we have the naturals, we have the rationals, we have all these different infinities. And the question is, are they all the same infinity? Like, are they the same type of infinity? Can we say whether one infinity is bigger than another, or are all infinities the same? Looking at here, it seems like maybe all infinities are the same. Let's look a little bit more. We really need to know, how do we compare sizes? That's our real question. How do we compare sizes? And counting doesn't make sense so much because we can't count to infinity. So how can we count without counting is the question. Yeah?
See how it expands? Natural numbers can only expand on the positive axis, but reals can expand both.
Right. So we can start thinking about how things expand. The naturals, for example, are certainly a subset, a proper subset even, of the integers, because naturals go one direction and the integers go positive and negative. That's one way to think about it. Yeah? So the suggestion was to take inspiration from ancient counting. That is, mappings. Can we map? Can we pair things together so that there is a correspondence between things? If we have two sets, if we can draw lines between them that pair them up, that means those sets are the same size in some sense. So counting doesn't make so much sense when we have such large things, kind of not uncountable, infinitely sized things, but we can start talking about mappings as a way to say how big two things are. So, for example, if I have 1, 2, 3, and x, y, z. Let's call this set A and this set B. We're going to start finite, because that'll build some of our intuitions. Are these the same size? Yeah. Why do we know they're the same size? Even if we didn't know what 3 was, even if we couldn't just look at this and say, well, that's 3 and that's 3. We can say, well, you can correspond them to each other. This maps to this maps to this maps to this. So let's look at more of an example of some things that maybe aren't the same size. So let's look at 1, 2, 3, W, X, Y, Z. Are these the same size? OK. Let's call this set A and this set B. Why aren't these the same size? What happens if I try to map here? We don't have much formal language yet, but like intuitively, what happens if I try to make a mapping from A to B here? What goes wrong? Yeah?
At least one of the elements of B goes unpaired.
Yeah. No matter, exactly. One of the elements must go unpaired. No matter how I match it, here's one matching I could do. It could be others, but no matter what, one of them is going to be left out. If I try to map the things in A to the things in B, I don't have enough elements here to match everything. I'm going to leave something out. So in this way, we can say that the size of A is less than the size of B. There's going to be something unmapped to on the B side. And now our last example is, let's say we have 1, 2, 3, 4, and we have X, Y, Z. Similarly, what's going to go wrong here? If I try to map the things in A to B, what's going to be the problem? Yeah? Mm-hmm?
Something in B is going to be pointed to twice, or some element in A will point to nothing.
Exactly. So if we try to map A to B, what's going to happen is, well, let's say I map 1 to X, 2 to Y, 3 to Z. Well, 4, no matter what I try to map 4 to, it's going to be a collision. There's going to be 2 things mapping to Z. Right? That's because there's too many things in A and not enough things in B. There's going to be a collision because B is smaller. We haven't talked about the pigeonhole principle, but this is basically how the pigeonhole principle works. If you have too many things, 2 things are going to collide. And this is the case where A is greater than B. Great. So this helps us give our intuition, but let's actually give a definition to things. So how we're going to count is with mappings, and a mapping is called a bijection. This is going to be one way to show 2 things are the same size. 2 sets, A and B, have the same what's called cardinality. That is just the size of a set is what's called the cardinality of a set. 2 sets have the same size. If there's a mapping from A to B, that's a bijection. And a bijection is just something that has 2 properties. It's onto, and it's 1-to-1. So I'm just going to write out the definitions, and we're going to reason about them. But what it means for something to be onto is that, oh, OK. I guess I'll just write it. Something to be onto is that everything in B, you could choose anything you want in B, and there should be something in A that maps to it. That is, for every B in B, there's something in A such that f of A equals B. Right? We don't want anything left out. 1-to-1 is kind of what it sounds like. Onto and 1-to-1 are actually pretty good names. Sometimes it's called injective and surjective, but onto and 1-to-1 are pretty descriptive. And 1-to-1 just says that anytime you have 2 things that map to the same thing, well, no, you didn't, because no, you didn't. This is what 1-to-1 says. If you have 2 things that map to the same thing, actually, they must have been the same thing. You can't have 2 things colliding. And this is how we typically show uniqueness. Remember, I'll make that prime bigger. This is how we show uniqueness, is if there's 2 things that we thought were different, A and A prime, actually they're the same. So in this case, what breaks here? Onto or 1-to-1? Who thinks onto? Who thinks 1-to-1? OK. Yeah, I'm seeing more hands for onto. And yeah, so onto does break here. Why? Because Z doesn't have something mapping onto it. There's something left out of the mapping, and that in this case is Z. This one then would be 1-to-1. Here's the collision. That's what breaks. I'm going to call it 1-to-1, 1-to-1. That's nicer to write. This is what breaks in this case. So this is a way to talk about sets being the exact same size. For finite sets, it's nice. There's a nice picture to it. We're going to start talking about it for infinite sets. Real quick, though, back to this original example, the reason why we said this works, this mapping works, is because each goat has a rock and only one rock. Each goat has a rock. Wow, this doesn't work that great. Each goat has a rock. Is that talking about onto-ness or one-to-one-ness? Who thinks one-to-one? Who thinks onto? OK, pretty split there. So each goat has a rock. We're mapping from rocks to goats. In this case, this means onto, right? Every goat should be mapped to by a rock. And only one rock means that there aren't any collisions. There aren't two rocks that collide to one goat, because that would mess up our count. So only one rock. This is applying to 1-to-1. Or that's what that's talking about. That's 1-to-1. So this is our way of counting now when we're counting infinities, which is a wild thing to do. OK, yeah, great. Great. So let's actually start proving things about infinities then. Yeah, let's erase Hilbert's Hotel. That was our nice informal example before we do real proofs. All right, so here's a claim. The claim is there's as many even numbers. Yeah, there's as many even numbers greater than 0 or greater than or equal to 0 as the size of the natural numbers. One way to say that is that 2 times n, this is the even numbers. This is n times 2. So this is the set of all even integers, or even positive numbers, is equal to the size of n. This is kind of a weird, yeah. So I guess we didn't define this. 2n is going to be the set 2 times k for k in the naturals. Right? That's what 2 times the natural numbers means notationally. It just says take every natural number, multiply by 2. So this is the definition of an even number. These are going to be all the positive even numbers. Does that make sense? Great. So this is kind of a weird statement. I mean, let's see how weird it is, because here's what 2n is. It's going to be 0, 2, 4, 6, 8, and so on. While n, the natural numbers that we all know and love, is just 0, 1, 2, 3, 4, so on. And what's weird about this is that we know 2n is a proper subset of n. Right? Like 0, 2, 4, 6, 8. Well, there's 0, there's 2, there's 4. 6 will be over here. 8's over here. This seems like it's double the size of that. Yeah? This seems double the size of that. Like it has everything it has, and then the odd numbers as well. So how can they be the same size? And I mean, here's the kicker. Like, can we see a mapping here that takes every element of 2n and puts it onto n? Yeah.
1/2 of that.
Yeah, exactly. So we can just do this mapping right here. We can just say 0 maps to 0, 2 divide that, and you get 1. 4 divide that, you get 2. 6 divide that by 2, you get 3. 8 divided by 2 is 4. So what we have here, let's actually write out what the bijection is. if we want to say that these are the same size, we want to say that there is a function f that goes from 2n to n. And we want to say that what this is and that it's a bijection. So what was just suggested is that if you take an x, what the function is you just divide by 2. That's the mapping. And the question is this a bijection? As in, does it do the same thing as with our rocks and goats? Does it pair them up so that there's one rock to one goat and exactly one rock? So what we need to do to show that, I'm going to erase this, is to show that f is onto and one-to-one. So first off, we're going to show onto. And we just need to look at the definition for that. We want to say that everything in n gets mapped to by something here, right? So yeah, let y be in n. What we want to show is that there exists an x such that f of x equals y. And not just any x, x into n. Let me rewrite this. X into, x into n such that, we're going to section that off. Right. So if we have, let's say, for example, let's say we have 26. 26 is a natural number. Do we know what number from 2n maps to that? Or, OK. I'll just come up with a new number then. Let's say 11. Let's say 11's in n. Do we know what number maps to that here? Yeah.
22.
Yeah. 22, f of 22 is what? It's just going to be 22 divided by 2, and that's 11. So this is just saying if you choose any number in the natural numbers, there's going to be something that maps to it. Let's look at this more generally. Well, right. All we need to do is show that there exists an x. So this is proof by example. The example here is, let's say set x equal to 2y. Now we see that f of x is equal to x over 2, which is the same as 2y over 2, which is y. How do we know that x is in 2n? How do we know that this was something that was in the original set that we're mapping from? Yeah.
Because y is in n, and 2n is just all the elements of n multiplied by 2.
Y is in n. This is just the definition of the even number, right? And this is all the positive even numbers. So we found an even number that maps to what we were trying to do. So this is our proof that that function is onto. That is the function that just divides by 2. And we're going to show one-to-one as well. And one-to-one, again, is kind of is the proof of uniqueness, right? That there's no two things that map to the same thing. So the way we always prove uniqueness, we've seen this a few times now, is assume there's two things, x and x prime. Let's say there's x and x prime in 2n. And what we want to show is that they're really actually the same. X and x prime have to be the same, right? Oh, sorry, I didn't finish this. Say that x and x prime are in 2n such that f of x equals f of x prime. Right? If we have a collision, we want to show that those were actually the same thing, so there's no collision. Right? That's what one-to-one means. And really, we just need to play with the definition. So if f of x equals f x prime, well, the definition of f says it's x over 2. And that's going to be equal to x prime over 2. Just multiply by 2 on both sides, and we get x equals x prime. Right? So this is just us stepping through what it means for a function to be onto and one-to-one. This is a proof of a function being onto and one-to-one. Making sure if we have something, again, onto means everything in here should have something mapped to it. So that's what we did. We chose something on the right-hand side and showed that we can find something on the left-hand side that maps to it. And then for one-to-one, we just want to show that if any two things collide with the function, they were actually the same thing. There was no real collision. So what this says is this, that there are these two sets that can be paired like rocks and goats. You know, they're exactly the same size. Why? Because infinity is kind of weird. It has enough room, like Hilbert's Hotel, to fit other infinities inside of it. So let's look at another one. Yeah, what do we want to erase here? I don't think we need the goats anymore. No. So now let's look at some other infinities. Let's say the natural numbers and the natural numbers versus the integers. There was this thought of, you know, like, the integers look bigger than the natural numbers. I mean, so did the natural numbers over the even natural numbers. But, like, you know, this kind of expands. It has the positive side and the negative side. How do you deal with having a positive side and negative side when the natural numbers only has the positive side? So the question is there an f that takes n to z such that it's a bijection? Can we create a bijection that says every natural number has a corresponding integer? Yeah.
You could start expanding from 0 itself for the integers because they expand on both directions. So for natural numbers, you can list 0 through 1, 2, 3, 4, and so on and so forth. For integers, you could do 0, -1, 1, -2, 2, and then expand with that.
So yeah, one way to think about it is, yeah, this kind of sense of enumerating or listing. What we're talking about is something called countability. We'll say what that is in a moment after we finish this right here, but it has the word count in it, but it's very different from the counting lecture. We're talking about something very different. We're not counting finite sets. We're trying to tell different types of infinity apart. Yeah?
Wait, is it that if we can prove that there's a onto and one-to-one relationship, then we prove that the two sets are the same size?
It is a definition of size. What we're showing is, this is called cardinality. The definition of cardinality is a notion of size for sets. And bijection gives us a measure of how big a set is. If you can make a bijection between the two sets, we say those two sets are the same size.
I didn't see what was the difference in the proof between the onto and one-to-one.
Right. So onto and one-to-one are asking two separate things. Onto is saying, choose something, again, let's make them a little bit different than 2n and n. Those are too close to kind of pattern match. But let's say onto says everything in B you should be able to find something in A that maps to it. So that's what we did here. We said start on the right-hand side, n, and see if we could find something from 2n that maps to it. And that's what we did. The second thing, one-to-one, is saying that we shouldn't have any two things mapped to the same thing. So those are just two different things we're trying to prove. And yeah, the way to prove it is always looks like this. That is, start with something that B, start with something in B, and show that something in A, we want to show something in A that maps to B. And one-to-one always says, take two things in A and show that if they map to the same thing in B, they were actually not two different things. This gives us, really what it gives us is this. We want to rule out these two cases. We don't want there to be anything left over, and we don't want this to be so big that it can't get onto B without crunching itself into it, right? Okay, so n to z, there was, this countability. Really, the natural numbers are 0, 1, 2, 3, 4, all the way down. So really, if we can set up a bijection from n to z, what we're doing is we're saying we can enumerate all of z in just a list, 0, 1, 2, 3, 4, 5, all the way down. This says that z is countable with the natural numbers. So let's see what that looks like. We were given kind of a description here. And yeah, I think we'll just need to go to the description that was said. But really, z is bigger, like was said. It seems bigger, that there's the positives and negatives. So we need 2 infinite buckets in n to catch all of those. So where do we get 2 infinite buckets? One suggestion was you have the evens and you have the odds. Those are 2 infinite buckets. So let's try to use that. I'm going to define f right here as 2 things. It's going to be x over 2 if x is even. And it's going to be, let's say, negative x plus 1 over 2 if x is odd. These are my 2 infinite buckets. There's infinitely many even numbers in the naturals, and there's infinitely many odd numbers in the naturals. And hopefully that gives me my positives and my negatives. There's my negative right there. Right? So let's see what this looks like. If we map out, well, we have 0, 1, 2, 3, 4, and so on. And the integers, there's a lot of ways we could write it, but one way we could write it is, well, let's see what happens here. 0, if I plug 0 in here, what does that map to? 0 is even, so 0 over 2 maps to 0. If I plug 1 in here, let's see, 1's odd, so 1 plus 1 is 2 over 2, that's negative 1. And OK, if I plug 2 in here, what's that? 1, exactly. 2 is 1, so 2 is even, so 2 over 2 is 1. And really, what we kind of get out of here is 1, we get negative 2, we get 2, and so on. So if we look at what that mapping does, I know we're going very fast here. It is this mapping here. So this is what it means to be countable. If you can map the natural numbers to something, you can enumerate them. So that is, here is z. It's 0, negative 1, 1, negative 2, 2, negative 3, 3, so on. We can line them up in one-to-one correspondence, like goats and rocks, to the natural numbers. That's what a bijection gives us. So even though it seems like z is bigger, indeed, the natural numbers are a proper subset of the integers. N is still infinite enough that it can capture all of z. OK, so we want to show some things. So let's go ahead and do that. First, I'll give a definition. A set S is countable. What that means is that there exists a bijection, which is specifically from the natural numbers to S. We can say S is countable if you can enumerate it. That is, they're a bijection from the natural numbers to S. You can write it out like this, just in a list. Okay. So I do want to get to something, because in the discussion tomorrow, you'll get to it. There's another proof we're not going to do right now for time, and it is that the size of n is the same at, and this is actually a little bit surprising. Well, all of it's kind of surprising, but this especially so, is the same size as the rationals. I'm sorry we don't have enough time to see how surprising that is, kind of lead up to it. But the rationals, there seems to be a lot of those. They're dense. You know, those are dense. But you can make a mapping from the naturals to the rationals. The notes don't really go into a proof of it. They do a proof by pictures. So I'll just give you that proof by pictures without a proof. We can do a proof, but we're not going to. And if x is in the rationals, by definition, what does that mean? It means there exist mn in z such that x is equal to m over n. That's what a rational number is. It is a fraction of two integers. It's a fraction. And one way we can look at the rational numbers, m by n, is that there's two integers here. We can kind of think of it as, well, here's all of our possible m's, and here's all of our possible n's. So if I have 1, 2, 3, and so on, 1, 2, 3. If I look at the coordinate 2, 3, what does that correspond to? That is the coordinate 3, 2. If that's my m and that's my n, what I'm saying that means is that that's 3/2. Right? 3, 2 represents 3/2. And how can we take this two-dimensional grid and make it countable? And there's really not time to show it, but you can make a spiral. So yeah, the notes don't do much more than this as well. It's a gnarly function if you try to write out what that function is. But what it does is it lets you do what we did a moment ago. That is, make it countable. That is, if you line up the numbers 0, 1, 2, 3, all the way down, what you're going to have is you're going to hit every rational number that exists in order. Not in the order of the rationals, but in a order. And that's going to hit every single one of them. That's a proof by pictures. It's surprising. What we really want to get to is where things get really surprising, actually. So, yeah. The rational numbers are countable. That's what this is saying. The size of n and the size of q are the same, is saying that there is a bijection between n and q. The rational numbers are countable. By doing this kind of spiral thing, you could hit all of them. Surprising, bizarre. We're going to see something even more bizarre. Because so far, what have we shown? We've shown that that yaha na'a game was pointless. Everyone kept trying to one-up each other with infinity, and they were all the same infinity. None of those infinities were actually any different. What's going to be really surprising here is there are infinities that are different. Yeah. What's that? Oh, yes. OK, it's not a bijection. This is true. There's another way to count things, Schroeder-Bernstein. And it says you don't need one-to-one and onto. If you could show that you have one-to-one one way, A to B, and one-to-one the other way, B to A, then Schroeder-Bernstein, the notes don't go over it either. They show if you have these two functions, you can create a bijection from them. We're not going over that, but really it's saying that if you get A to B one-to-one, that's kind of like A being less than B, the size of A being less than B. And if you showed both ways, A and B, the size of A and B are equal. So this is going to be unfortunate. What I'm going to show you is that R is uncountable. And we're going to have to just race through this. But this is kind of as surprising as it gets. That is, the reals are just too big. They're just too big. You can't count them. We're going to show even more than the reals, just the real interval, 0 to 1. Just the reals in between 0 and 1, that's not countable. So how do we show this? By contradiction. And I'm just going to have to tell you, it's going to be blazing fast. Let's say we did have a list, 0, 1, 2, 3, 4, so on. We have this big old list. And let's say we had all the real numbers possible. We had, I don't know, maybe 0.5, 7, 9, 2, 3, 1, 3, 4, so on. Here we have 0.1, 3, 4, 7. You know, we have all these different real numbers. And let's say we think we had all of them. By contradiction, I want to show there exists x not on the list. That is x being in 0, 1. And I'm just about out of time. I'm going to say what x is going to be, I don't want it to be on this list. I don't want it to be here. So I'm going to say, well, let's take 0.5 and say, actually, it starts with 0.6. And this has 3 right there. I'm going to say, actually, I want that to be 4. That is, I'm just adding 1 to there. So it's neither this element or this element. And let's say there was a 7 here. I'm going to say the third element is 8. And the third right here, let's say that was 1. I'm going to say that's 2. Let's say this was 9. I'm going to say that's 0. So I'm just kind of making a diagonal here and saying, let's disagree everywhere. Let's construct an x that disagrees everywhere. And the problem here is if we have x down here, what happens at its diagonal? This is the contradiction. If you construct x that flips things on the diagonal so that it doesn't agree with any of these, you'll end up with an x that can't agree with itself. As in, x can't exist because it must exist somewhere on the list if it was part of the list, and you constructed it so that it breaks itself. It can reference itself and breaks itself. So it's sad how fast we had to go through this. It's quite a wild topic, but this technique is called diagonalization.